Good morning. First, I'd like to thank very much the organizer for inviting me to this interesting workshop. Well, this time I'm going to talk about our recent work on multiscale finite element methods for some sign-changing problems. And this work is in collaboration with Jim, who is my student, and Patrick CLA from this center in Paris, and also Ye, who is also my postdoc, I think, right now. So in this talk, I'm going to go over the method and also the analysis of the method, and also show some simulation results. So first, I will mention some introduction. So we start with metamaterials. This kind of materials offer unconventional properties, quite unusual, and is not found in nature. This type of metamaterials are typically created by combining some common materials in some periodic way. And so there are some mathematical homogenization theory for this kind of problems. And for example, in these two figures, we illustrate some example of metamaterials. For example, the one on the left-hand side, this type of material gives negative Poisson ratio, and this one on the right-hand side gives nearly zero shear modulus. Another type of material is this type of negative index materials. And typically they have negative reflective index. And this means that the light will bend in the opposite direction, as you see in this figure on the left-hand side. And this kind of materials can be used to create superlens and invisibility cloak. And in terms of PDE analysis, this will also give some new research direction, as typically the PDE is not well posed in the classical sense. So next, let me talk about the model problem that we consider in this talk. So this is the typical PDE that we consider, and U is the solution. And for simplicity, we assume that it is zero on the boundary of the domain, and sigma is the material coefficient. And then we assume that the domain omega is divided into two non-overlapping subdomains. We call this omega plus and omega minus. And then for the problem we consider, we will assume that the coefficient sigma is positive in omega plus and is negative in omega minus. Okay. So this is the model problem that we consider. And then the standard bilinear form for this problem can be defined similar to the classical sense. Okay, so AVW is defined in the same way as before. And then this space capital V is also defined in similar to the classical problem. But the main problem is that this linear form is not cohesive in this space capital V, okay? Because its sigma can be negative in some subdomain. And then a main mathematical tool to study is this T-coercivity theory, according to this, introduced by these authors. So next we talk about the variational form of the problem, and it is defined in this way. And then we find the solution U in this space B, which is H10, and Now, about this T-coercivity, this is the definition. If we can find a projective map T from capital V to V, okay, such that this inequality holds for a positive constant alpha, then we say that this bilinear form satisfies this T-coercivity condition. And then this energy norm on the right-hand side, we used a tilde to denote this energy norm, and it's defined using this definition. And the consequence is that if this T-coercivity condition holds, then we can obtain this inf-sup condition for this bilinear form A, and this with this positive constant alpha. So next, in order to construct this mapping T, so the typical trick is to introduce a flip operator R, and this flip operator R will map a function defined in omega plus to a function in omega minus. Okay, this is the definition. And we also require that along to the interface between the omega plus and omega minus, this R is the identity. Okay. So once we have determined this map R, and then we can define T like this. Okay. So in omega, we can write V in this way. Okay. V is V1 in omega plus, and V is equal to V2 in omega minus. And then T can be defined like this. So in omega plus, it is the same, but then in omega minus, we use this formula. It's negative V2 plus 2 RV1. And so this is the definition of this mapping T. Once we have defined this T, and then we can use a very simple idea to show this T-coercivity condition. So the idea is, as you can see, that is very simple. So of course here we apply the definition of, so we first split the omega into two parts. One is omega plus and then omega minus. And over here we apply the definition of this mapping T. And then basically after you apply some Young's inequality and so on. And at the end we can show that this AV, TV is bounded below by this number multiplied by the energy norm. Okay. So you see that this number depends on the contrast of the coefficient in omega plus and omega minus. Okay. So this is the maximum absolute value of the value of sigma in omega minus, and this is the minimum value of sigma in the domain omega plus. Okay. And so which means that if this number is small enough, you get coercivity. So that's why we mentioned that if the contrast ratio is sufficiently, so here we change the order of the coefficient. So if this ratio is sufficiently large, then we say that this model problem is well posed. And here we give an example of this mapping R. So here we consider this flat interface model, and then the interface is defined by this value gamma. And then this flip operator R can be defined like this. Okay, and then we can show that this norm is equal to this, and then we can apply the T-coercivity idea. So next so in this talk we will consider multiscale computational method, and because so for this problem the coefficient can have a lot of heterogeneities, and also the contrast can be very high due to the design of the material and also the well-posedness of the original reading. And of course, there are a lot of different multi-scale methods that are developed, here we have the multiscale finite element method, and also the generalized multiscale finite element method, and the LOD method, CEM-GMsFEM, and also this multiscale method that we developed. And so actually, let me mention that there's a very interesting work by Barbara using the LOD method to solve this type of sign changing problems. And this is the reference. And then in our work, we will apply this type of generalized multiscale finite element methods. And for this method that we developed, the eigenvalue problem are one of the important steps in the construction of multiscale basis functions. And of course, once we have constructed the multiscale basis functions, then the final problems that we solve are relatively small and can be solved efficiently. Okay, so next let me talk about the method. So first we will start with the mesh. So we will consider a pair of meshes. We call this K little h and K capital H. This K little h is the phi mesh, and this mesh should be able to resolve the heterogeneity of the coefficient sigma. And for this figure on the left-hand side, this little element here is the phi mesh. And also, when we compute the multiscale basis, we will also solve some local problem. And to numerically solve the local problems, we will also use this phi mesh. And then to solve the final linear system, we will construct some multiscale basis on the cos split. Okay. And for our method, we will need to define some oversample regions, KIM. So for example, in the basically Ki is a cost element, and then we can define oversample region by extending the cost element Ki by this m means by m cos split layers. So for example, if this is Ki double prime, then this region is Ki double prime 2, because we extend this cost element by 2 cos split layers. Now, let me mention that in the original version of this generalized multiscale finite element method, we consider this local spectral problem for each cost element Ki. Okay? So you see that the left-hand side is this bilinear form for the elliptic PDE, and then the right-hand side is some type of weighted inner product. Okay, it's weighted by the coefficient sigma and also some other parameters. And then the original, the idea in the original version of this method is to define a space by using the leading eigenvectors. This means we use the eigenvectors corresponding to the first few small eigenvalues to construct and space. But then so for this problem that we consider, the coefficient sigma is not uniformly positive, and which means that this problem may have some trouble, and we need to modify the construction. So that's why we consider this new way to define the eigenvalue problem. As you can see here, we put the absolute value on both the left-hand side and the right-hand side. And but then, of course, you observe that if the coefficient sigma is either -1 or 1, then of course this problem becomes a trivial eigenvalue problem. But in this case, the PDE is not well posed. So that's why by using the absolute value sigma, we are still able to include some of the heterogeneities in the eigenvalue problem. And then we use this notation, psi I j, to denote the jth eigenfunction of this eigenvalue problem for the cost element ki. So next, we will define the multiscale basis. So first, we collect all these local eigenfunctions, and then we call this the global auxiliary space. Okay, this is the notation. And then next, using the and of course here we also have some. So next, we define this projection operator pH. Okay, which is the so we will project some function to the space VAUX. Okay? Just the L2 projection, and the L2 projection is defined using this weighted inner product S. Okay, and then you see that this mu is the weight. This mu is usually chosen according to sigma. Okay, so this is the weight, and then we can use this inner product to define this projection map from some function space to the space VAUX, which is a linear combination of these local eigenfunctions. So next, we will define the multiscale basis. Okay, and we define this for each eigenfunction that we selected. Okay, psi ij, and for each psi ij, we solve this local problem to get the multiscale basis phi ij, and then this phi ij is belongs to this space VIM. You see that this VIM is defined in this over sample region with zero boundary condition. Okay. And then this basis phi satisfies this variational problem. Okay. So this A is restricted to the over sample region, and also this L2 in the product is also restricted to the over sample region. And you see that the projection operator is used over here. And on the right hand side, you see that this is the given eigenfunction, which is defined only on Ki. So that's why this is only defined on Ki. Okay. And this is the definition of the multiscale basis. And then this is a summary of the method. Okay. In step 1, we for each cost element, we solve this local special problem to get a set of local eigenfunctions. And then once we have these local eigenfunctions, and then we can define this projection operator P, which is map any function to linear combination of these local eigenfunctions. And then using this operator pH, and then we can solve this local variational problem on oversample domain to get the multiscale basis. And then we can collect all the multiscale bases to form the multiscale finite element space VHM, and this M means the size of the oversample domain. And then at the end, we use this space to solve the variation, to solve the PDE. This is the summary of this method. So next, of course, the motivation of finding the basis function in that way is that the multiscale bases have some nice decay property. So here we illustrate this using this figure. So this is the coefficient sigma, and we consider this cost element. And then in this 3 figure, we basically show the first 3 eigenfunctions. And then next we will see that we will see the image of the basis function. So in the first row over here, we show the first multiscale basis, the first multiscale basis, and then we also consider 3 oversample regions. Okay? For example, this is for m equal to 1, this is m equal to 2, this is m equal to 3. And you see that the basis is basically quite local within this region. Okay? And then the same thing holds for the second and also the third basis. Okay? And this, again, this is the reason we construct the basis function in the way that I just mentioned. And also we have some theoretical result. Okay, so so of course I'll come back to this later. It basically shows that if you compare the multiscale basis defined on oversample region with size m, and compare this with the basis function that you solve within the whole domain, then you see the difference is bounded by this quantity. Okay, you see there's a theta to the power n minus 1, and this theta is a constant that is less between 0 and 1, and then again m is the number of oversample layer. So which means that you see that outside. So once you have choose m large enough, then you see that these two functions have very small difference. Now, so here we discuss some type of analysis. Following the LOD idea, so we also first consider the global version of the basis. Okay? So this means that for each eigenfunction psi, okay, so we solve this function in the whole domain, okay, and this V is defined in the whole domain, and then you see that we solve a similar problem, but then this is defined in the whole domain, and then we are able to obtain two results, okay. The first one is that in order to solve this problem, we will need some type of well-posedness for this variational problem. And then we can show the inf-sup stability of this linear form using the T-coercivity theory. And again, this gives you the well-posedness of this problem. And then next, so for this space, V infinity. So this means that we collect all these global functions, and then we form this space. Now, and using this space, we can solve the original problem. And in order to solve the original problem, we also need some type of inf-sup stability for this space V infinity. Okay? Again, this makes sure that if we use this function to solve the original PDE, we get some well-posedness. So again, of course, here in order to show that this again here we consider we want to say that this problem is well posed. Okay, this A plus S is well posed, and then we so the idea is that we need to. So here we basically apply the T-coercivity theory in some suitable way. Okay, and then we show that this bilinear form A and also this bilinear form S satisfy these inequalities. And then the main idea is that we will have to assume that this is a contrast. Okay? This number is the contrast. Should be large enough. It should be bigger than some number. Okay, and this is because of the well-posedness of the original PDE. Okay? So the contrast should be high enough. And also there's another condition that this epsilon is small enough. Okay, so let me point out this epsilon comes from the eigenvalue problem. Okay, this epsilon is 1 over the eigenvalue, and again this means that we have to make use of sufficiently many eigenfunctions so that this 1 over the eigenvalue is small enough, because usually we will use the first few eigenvalues that are small. Okay, so this epsilon should be so you take 1 over lambda, and this typically this involves the eigenvalue that are not used. So if we make use of all the small eigenvalues, then this 1 over lambda here is not it's not that large. Okay, so that's why we have. So this condition also tells us that we need to make use of enough eigenfunction, and then combining these results, we show that this problem is well posed. Okay, and also another important idea that we use in the analysis is some type of orthogonality condition. Okay, so here I basically say that if we define this space W to be the kernel of this map PH, okay, that we defined earlier, and again this V infinity is a space that contains all the global basis functions, and then we can say that these two spaces satisfy this condition. If V is in V infinity and W is in W, then they satisfy this condition. And on the other hand, if for any W, such that this is true for any V in V infinity, then this W will be in the space W. Okay? So let me point out that again, this is the one of the key steps that we use in the analysis, and of course we also this is motivated by the LOD analysis. So let me point out that because A is not so this A is not inner product in the classical sense, so this is not a real orthogonality condition. Okay, and then to prove this, we also have some other steps here. And then after that, and then in the second part of this theory, we also show that this V infinity space satisfies this inf-sup condition. And again, this makes sure that this, if you use this space to solve the original PDE, it is a well-posed problem. And also involve a few steps. And one of the main steps is that we have to modify this T operator in the T-coercivity theory, and then we modify this, and then make use of this modified operator T to show the T-coercivity. Maybe I won't go too much detail. And then combining all the previous results, and for the global solution, again, this U is the original solution, and then this U infinity is the solution that we obtain by using the space V infinity. Okay? And then we obtain this error bound. And again, we have some assumptions that the contrast will be large enough, and also this epsilon should be small enough. And this means that we have to use sufficiently enough eigen functions to construct the space. And then you see on the right hand side, you have this cost element h here, and then multiplied by this value depends on sigma, and then the 2 norm of the source term. And then the proof is also so for this global version is also quite simple. We just basically if this E is the error, so basically we just make use of the 2 steps that I already mentioned. One is the inf-sup condition for the space V infinity, and then next another thing is this orthogonality condition. So we basically make use of these two steps together with the eigenvector expansion. So basically, we make use of these three ingredients to show that the error is bounded by this quantity that we need. Okay. And the next, let me go to the local basis. Okay. So for the local basis, we obtain this error bound. Okay. Again, this UM is a solution by again, this M is the size of the oversample domain. Okay. Again, this means we use local basis to solve the PDE, and then this is the bound. And then you see that there's a constant theta that appear here, and this number theta is between 0 and 1, and it's independent of the mesh size h, and also independent of the layer width m. So basically, you see that we have, and also this condition tells you that you have to take m large enough so that this part of the term here is small enough. And to show this theorem, we have to make a technical assumption, which I will discuss. So one technical assumption is that we have to assume that the cost element satisfy this type of condition, which means that the cost element is either in omega plus or in omega minus. Okay. This means that the cost mesh, we solve the interface between omega plus and omega minus. And we make this assumption because in some part of the analysis, we have to make use of this trick, otherwise it seems not so simple to remove this assumption. And this assumption is also used in some other works that they need to construct these flip operators. But then for our numerical results, it seems that we do not need such assumptions, because we can, for the numerical results, we are able to use more flexible cost grid. So another assumption is the following. So so basically is number 3. We have to assume that this mapping T, okay, satisfies this condition. Basically, if the support of some function V is inside some oversample region, then T of V, support of T of V should also be inside the same oversample region. And this is one of the technical assumptions that we have to make. And I think it's also something similar in this work over here. Basically, this is the key assumption. But then for the numerical simulation, we think that we do not need such assumptions. And then next, let me comment on this constant theta that appears in the error bound. So it basically depends on some constants, okay? And these constants are basically quite robust when the contrast is sufficiently large, and also we have epsilon sufficiently small. And again, this means we use enough eigenfunctions. And then this number theta is something that is not close to 1, and which means that we have a good error bound. And then there also this is basically shows the localized property that I discussed earlier. So basically, what we show is that if you consider the global basis, okay, this G infinity is the basis that we form in the whole computational domain. And if you look at the value of this global basis outside some oversample region, and it is small, okay, because it is bounded by theta to power m. Okay, again, this theta is bounded away from 1. Again, this means that if you choose M a few layers, then this number is already small enough. And then the analysis is basically based on quite standard steps that and then this is the final result. Basically, we compare the two bases. One is the global and the other is local, and then we get this final bound, which depends on theta to some power n minus 1. And for the analysis, I will. Well, and then maybe I also mentioned that to show the final error bound, okay, for the approximate solution using the local basis, we basically the use of the CS lemma, and then we just divide the solution into two parts. One part comes from the solution using global basis, and then the second part make use of this localized error bound. And then combining these two steps, we get the final error bound. And of course, here we also make use of the special problem that we consider, because for this final step, we will have to make use of the eigenvector expansion. Okay, so next, let me show some numerical results. Okay. So first, I consider the flat interface model. Okay, this is the model that I considered earlier, and then I basically consider the coefficient, which is like this. So in the omega plus, it is 1.01, and in omega minus, it is -1. And then this is this corresponds to these two figures, A and B. Okay. Now the first observation is that as we find the cost element, we see improved results from our method. Okay. And also for this case, because we take gamma equal to 1/2, this means that the cost grid we solve the interface. So in this case, you also see that if we use the Q1 element, this is the standard Q1 element. So you see that the Q1 element also gives you a nice result in this case, and sometimes even better. Okay, this is the blue line. Because the grid match with the interface. And then in the next two figures, we show the case when sigma is 1 in omega plus, and sigma is equal to -1.01 in omega minus, and the result is similar. And then in this second case, we take gamma. So gamma is this line on this horizontal line. Okay. So in this case, the cost grid does not resolve the interface. Okay. So in this case, you see that this Q1 element does not work well. Okay. So the error is large in this case. But then for our method, we can still produce accurate solutions. You see that the errors are much smaller compared with Q1 element. And we also see convergence with respect to cost bit size, and also as we increase the oversampling layer, we also see improved solutions. And if you look at the pointwise error, these two figures shows the pointwise error is also quite small. Then in the second example, we consider this periodic model like this. So this is the source term, and then here we show two reference solutions. This one is for cost grid, which is 10 by 10, and this is solution for cost grid, which is 20 by 20. And here we look at the errors in terms of energy norm and also the L2 norm. And then as we find the cost grid, so according to the theory, we also have to increase the oversampling layer. Okay, so that's why if you look at these numbers, okay, according to the theory, we observe some convergence rate, okay, as we increase cost n. This is for this case, and then for the case when we use 20 by 20 cost element, we also observe some convergence rate as we increase both, we find cost element size and also increase the oversampling layer accordingly. So the third example is this model that we consider. This is the sigma, okay? And then we consider two cases. One is, in the first case, it's 1 in omega plus, and then in omega minus is negative 10 to minus 3. And then in the second case, it's 1 in omega plus, and then it's negative 10 to power 3 in omega minus. And these are the coefficients. So basically, we also basically consider the error with respect to. So here we look at the error in energy norm. This is this figure, and then this is the error in L2 norm. So in this figure, we in the horizontal axis we show the number of basis functions. Okay, so we see that here as we increase the number of bases, we obtain better results. And also, when we find the cost element, we also see nice results. And then for this example, we also show the corresponding eigenvalues. So you see that, so say for example, you see that if you consider the case when h is 1 over 10, then you observe that the second eigenvalue is very small. Okay? So this means that the second eigenfunction should also be included in the construction of the basis. But then the rest of you see that the rest of the eigenvalues are not small. And this means that you can skip those eigenfunctions. So here the main point is that you have to include these eigenfunctions correspond to small eigenvalue in order to have a robust bound, because this is related to this number epsilon. Okay, so finally some conclusions. So this talk we have developed a multi-scale computational method for some sign-changing problem using generalized multi-scale finite element method. And so basically we have to construct the local eigenfunction in some suitable way, and then in order to show the robustness and convergence, we make use of some ideas from T-coercivity theory, and then the resulting method is robust with respect to the contrast and oscillations in the coefficient. And then we have some numerical results that shows that the cost mesh doesn't need to resolve the interface, even though our theory make use of this condition. And also, example shows that it is robust with respect to the contrast and heterogeneities. With that, I'd like to thank you for your attention.